Hello everyone, I'm J Wildberger. In today's video, which is famous math problem number 18, we're going to be looking at the perspective image of a square. And the problem is to show that any quadrilateral is the perspective image of a square. What does that mean? So this is in the context of a very classical subject called projective geometry, which is a very rich subject with a lot of history, which unfortunately is not as well studied these days as it really ought to be. So it's something that a lot of students don't have enough familiarity with, and it's a chance for me to delve a little bit in a very intriguing and beautiful subject. Okay, so the problem is very practical. It's that we have, say, a square. Okay, that's a square. Okay, and we're working in three-dimensional space. And we imagine that we have, say in the plane somewhere, a quadrilateral. Can we see this quadrilateral as the image of a square from some particular vantage point called a point of perspectivity, say P? Okay, so this is the diagram. You're supposed to think about this as being in three dimensions. So that's one plane in three dimensions, maybe the plane of the board, say. And there's another plane, say the plane of the square. And then there's some point P out here. And we're looking with one eye closed, our eyes at P. We're looking at this square and superimposing it exactly on this quadrilateral. So we have a lot of freedom here. We can move the point of perspectivity around, and we can move the square around. And we're just trying to line things up so that the line joining the eye and a corner of the square matches to one of the corners of the quadrilateral. So 4 such lines emanating from the point of perspectivity. Okay, a bit of terminology. The plane containing the quadrilateral is the image plane. That's the image quadrilateral. The plane containing the square is the object plane. And the point P is the point of perspectivity. In some sense, projective geometry is a very elementary kind of subject because it really only deals with a straight edge, not a ruler, just a straight edge, and various incidences that we can obtain by drawing lines and their intersections to create points. So in the plane, the only ingredients are really points and lines to begin with, at least. The subject goes back in some sense to the ancient Greeks. There's really one famous theorem, Pappus's theorem, which is really a projective geometry theorem. But the subject really has its start around the 17th century, the work of Desargues, and then later Poncelet and the whole range of 19th century mathematicians who then further developed it. Pascal also made an important contribution. But it's a surprisingly elementary kind of subject. And unfortunately, students these days don't get any exposure with it. So just to get you on the page with projective geometry, let's play around a little bit with quadrilateral in the plane. And these will be some important ideas here that we arrive at. Okay, so here we have 4 points. Let's say a quadrilateral, okay? And if we have 4 points, and they're sort of in general position, so no 3 of them are collinear, then what can we do? Well, we have a straight edge, so we can start joining points. Let's do that, all right? So we join points, and in this subject, we typically join points with lines, not with line segments. Okay, so there's a line, and there's another line, and there's another line, and there's another line. We should meet lines when we can. All right. So those are 4 lines, but there's actually 2 more because there's also sort of these, you might call them diagonal lines, but in some sense they're just as good as the other lines. So altogether, really, the 4 points determine 6 lines. Okay? So I'm just going to record what we've done here. So we started with 4 points, okay? And now we've moved to 6 lines. Great. And now what happens? Well, now there's a few more points that we can see. So now we have this sort of meet of diagonals, but maybe we could also think about this one and this one. They all play sort of a similar role. Okay? So we might call these sort of the diagonal points of the original quadrilateral. So we have then 3 more points in blue. Now what can we do? Well, we have some points. We can join them to make more lines. So let's do that again. These 3 new points, we can join them to make 3 new lines. And this one also. Great. Okay, and I've also made them in blue, so that's 3 more lines that we've just done. Great. Now, is there anything else we can do? Well, if you stare at this for a little while, you'll see that there's actually some new points that come into being, because whenever we have 2 lines, we can look at their point of intersection or their meet. And so let's find these new points of meeting of the new lines that we've just drawn. So there's one right here. Maybe I'll make it little triangles, okay? There's a little triangle point. There's another one there. There's another one here. Oh, there's one there. Oh, there's one over here. And, oh, yes, the other one is off the page, which often happens in this kind of situation. So this black one here and this blue one here, they're almost parallel, but not quite perhaps. They will meet at some further black point way down there somewhere. Okay. So we have now just made 6 new points. And now something rather remarkable happens. Okay. So now there's some further thing that happens, and at this point here some magic suddenly appears. And the magic we will illustrate with going back to red. The magic is that these 6 points that I've almost drawn actually have a lot of collinearities. So that these 3 points are all on a line. And these 3 are on a line. And the other ones will involve point down there. Let me see. Oh yeah, these ones here. Okay, these 2 here, and that point down there will turn out to be on a line. And also these 2 here, and that point down there. Whoops, that point down there will also be on a line. So we get, if I squeeze it over here, 4 lines. At this stage we can pause because we have a kind of a closing of the circuit. Okay, we started off with 4 points, the original 4 red ones right here. And then we got 6 lines in black, creating 3 diagonal points in blue, creating 3 diagonal lines in black. Then 6 more points in black, and those points happily ended up lying on 4 lines. And now there's a complete, nice, beautiful symmetry here between the points and the lines. So this 4, this 4, this 6, and this 6, this 3, and this 3, nice symmetry. And if you had started with 4 lines, the 4 red lines, you could have done the same thing that I've done. It's a great exercise to do that. Start with any 4 lines and start cooking up points and then lines and then points and then lines until you finally get 4 points at the end. And you're basically reversing this process here. So, by the way, this is not the end of the story, because once you've done this, there's a lot more points. And there's all further kinds of questions to be studied, even with this seemingly very simple configuration. So it's actually a source of great potential research. Okay? I don't think it's adequately studied. So if you're an amateur geometer and you'd like to really get your teeth into some investigations, have a look at the general quadrilateral or quadrangle. By the way, quadrilateral refers maybe to 4 points, quadrangle to 4 lines. The symmetry between these terms, reflecting the symmetry between points and lines in the projective plane. Now, before mathematicians started studying this subject, actually artists had been working in this direction also already for several centuries. The Renaissance artists were interested in trying to come up with more realistic portrayals of three-dimensional scenes in their sketches, in their drawings, in their paintings. And so they actually developed rules which really are closely connected with projective geometry. And one key feature there is that when you're drawing a scene, a landscape or something, there's often a horizon. Okay? And if there's a horizon, then it has the property that lines which appear parallel when you sort of look at them close, when you look at them from a distance, they seem to converge to a point on the horizon, like railway tracks. Okay? And the perspective artists realized that these points, sort of at infinity, played an important role in trying to establish the right relationships in the things they were trying to draw. And I want to illustrate that because it's very pertinent to the problem that's at hand, the idea of seeing whether an arbitrary quadrilateral can be the image of a square. The Renaissance artists had sort of the reverse kind of challenge. They had, say, a tiled floor, maybe made out of square tiles, okay? And they wanted to represent that in a picture. So imagine the tiled floor is horizontal and it's in front of you like this, and maybe there's a scene, maybe there's people dancing on it or something, and there's furniture and such. But you want to represent that. Like if you took a photo of it, what would you see? And they realized that there was a certain technology that was actually quite subtle that allowed them to do this in a mathematically sound way. And I want to show you what that is because it's sort of relevant to this discussion. So here is the starting point of a painter's representation of a tiled floor. Okay, where he's decided to make a tile like this, and he's going to extend this thing to a picture of a tiled floor, which has square tiles. So how is this done? Well, these two lines here meet at a point, which is going to be on the horizon, because we're assuming these sides are actually parallel. And these two are also going to meet at a point which is on the horizon. So we know where the horizon is. Okay, it's determined by the meet here and here. Now, the critical thing is to look also at the diagonals of this quadrilateral. Okay, so if we look at this diagonal here, there's another point on the horizon, which is then the line or the direction of the diagonals. And if we go back to say the original tiled floor, we're talking about diagonals like this. Here the diagonals are all parallel. And that means that when we represent them on a picture, then all those parallel lines should meet at the same point at infinity on the horizon. Again, like railway tracks. Okay? So that means that, so let's say we've just drawn this diagonal here, starting from this point here. So that means that then if we're looking at the diagonal starting from this point, which would be this one here going up, the way we would draw this diagonal is to make it parallel to this one here. And what that means in the diagram is that we have to connect it to the same point at infinity. And while we're at it, we can do it also on the same side here. So what does this do for us? Well, it allows us then to find these new points, because then we now have some more points here and here. Okay? And then we can connect them with the vertical or the horizontal points at infinity to get some new tiles. Okay, so what we've accomplished now is to find three more tiles. Okay, so we've painted not just that one, but also that one, and that one. And we could carry on now because actually, for example, the next one is going to go through this. This diagonal is going to meet here and here. So let me just actually draw two more so you get a sense of what it looks like. Okay? And so you can see that a representation of this tile floor is being created here with this construction, and we could easily carry on. And it's a pleasing kind of thing. The eye looks at this, and if you put some furniture or some people on here, you really do get a sense of perspective, because this is actually what you would actually kind of see if you actually, looked at a big tile floor from a distance and took a photograph of it. Okay, so the Renaissance artists already had key ideas and technologies for projective geometers before the mathematicians got around to it. Now, another very important sort of ingredient in projective geometry is the idea of a cross ratio and the corresponding notion of harmonic points, harmonic ranges, and harmonic pencils. So let's start with this definition, that in the affine plane, if we have 4 points, A1, A2, A3, and A4, and they are collinear, okay, so they're all on a line, then their cross ratio, the cross ratio little r of A1, A2, colon A3, A4, is this number. Okay. The number itself is a ratio, there's a division here, a ratio of 2 ratios. And the ratios involved here and here are ratios of vectors. Okay, so we're using a bit of affine geometry, which is closely connected with linear algebra and the algebra of vectors. So here we have A1, A3 over A2, A3. So those 2 vectors are going to be in the same direction. So one of them is a multiple of the other. And so this number here is expressing the multiple that we have to multiply A2, A3 by to get A1, A3. And over here, same kind of thing. It's the ratio of A1, A4 to A2, A4. Let me illustrate with these 4 points, A1, A2, A3, A4. I'm putting them in this order for a reason, but actually the definition works no matter how they are arranged. So what are the ingredients in the definition for this situation here? Well, there's the vector A1, A3. Okay, so there's that vector A1, A3. And then there's the vector A2, A3. Okay, that's that vector there. So let's think about this ratio here. What's the vector A1, A3 divided by A2, A3? Well, this vector is about twice the size of that one, let's say, okay? But there's a change in direction because they're going in opposite directions. So this ratio would be -2. Okay, so this thing here would be -2. And let's look at this thing here, A1, A4. So that's this ratio, this vector here. Okay, that's A1, A4. And A2, A4 is that vector. So what's the relationship between these ones? Well, it looks like A1, A4 is, okay, maybe it's 3 times. Okay, so that this ratio would be 3. Okay, so then what would the cross ratio of these 4 points be? It would be -2 over 3. -2/3 would be the cross ratio. Okay, now there's a very special situation called a harmonic range. So collinear points A1, A2, A3, A4 form a harmonic range precisely when this cross ratio is -1. So this is a very key notion, this particular quantity here, because it turns out that it's a projective quantity. And to explain that, we have to sort of extend this one-dimensional analysis to the plane. So when we go to the plane, there's also a notion of cross ratio. And that, at the most simple level, has to do with vectors. So if V1, V2, V3, and V4 are vectors in the plane, then their cross ratio is defined by a similar kind of formula, but involving a cross product of vectors. So I have to tell you what a cross product of vectors is. It's something that's very close to the cross product of vectors in 3-dimensional space, but it's a purely planar story. And it's really just the signed area of the parallelogram formed by those 2 vectors. So here are 4 vectors, V1, V2, V3, and V4. And the cross ratio, which now has a capital R of the 4 vectors, is in terms of ratios of cross products. So what is the cross product, say, of V1 with V4? Say this thing here. Okay. So here's the vector V1, here's the vector V4. If we form a parallelogram by those 2 vectors, okay, there's a parallelogram, then the area of that parallelogram, or actually the signed area of that parallelogram, is V1 cross V4. Okay, so that's a geometrical way of saying it. More precisely, maybe I'll put it here. If we have the vector AB and we have the vector CD and we've chosen coordinates, okay, then the cross product is defined to be the number AD minus BC. So it's a determinantal thing which represents a signed area. Okay, so that's a formula for the cross product of 2 vectors once you've chosen coordinates. But if you don't want to think about coordinates, you can think about it as being areas of parallelograms, but suitably given signs, so it's sort of positive or negative depending on the orientation. If you're going from vector here to a vector here, then it's positive, otherwise negative. Okay, and the formula is a lot like the one that we've just seen for points. So this V1 cross V3 over V2 cross V3 divided by V1 cross V4 divided by V2 cross V4. So this looks the same as this, except that the 3's have been replaced with 4's. And a very important property of this number is that it's unchanged if any of the vectors are scaled. So if we multiply V1 by 5, then this numerator gets multiplied by 5, and this numerator here gets multiplied by 5. Since we're dividing, the 5's cancel. On the other hand, if we multiply, say, V3 by 7, then this numerator gets multiplied by 7, and that denominator gets multiplied by 7, and again, there's cancellation. So the cross ratio of these 4 vectors only depends on their directions and not actually on the sizes of the vectors themselves. So from that observation I've just made, we have a very important conclusion, which is that we can extend the idea of a cross ratio to 4 concurrent lines. So in the affine plane, if L1, L2, L3, L4 are concurrent lines, L1, L2, L3, L4, with direction vectors, say V1, V2, V3, V4 respectively, then their cross ratio is the cross ratio of the lines L1, L2, colon L3, L4 is defined to be exactly the same as the cross ratio of the corresponding direction vectors. Okay, so we choose direction vectors for the lines. Say there's V1, there's V2, doesn't matter what direction they're in. There's V3, and there's V4. Okay, so we choose direction vectors, we compute the cross ratio of the vectors, and then that's the cross ratio of the lines. So now we have a cross ratio of collinear points as well as concurrent lines. Now we have that nice symmetry that's so important in projective geometry. Look, I should probably also tell you that in most textbooks on this subject, even classical books, even books which are very good, there's often some logical confusion, okay, on the cross ratio. The reason is because there's a temptation to use lengths, to define the cross ratio in terms of lengths, rather than in terms of the cross product, as I've done. So this is a kind of an innovation that I'm proposing, and that especially figures in my Algebraic Calculus course. So these topics are things that do find their way into the Algebraic Calculus course, because the cross product of 2 vectors is absolutely fundamental for setting up the algebraic calculus. But so I should just warn you about that definitions of the cross ratio which involve lengths are unfortunate, and ones that that involve sines and cosines of angles are also unfortunate. You don't really want to do that This is the better way. Okay, so now we have the theorem which connects these two cross ratios. It's a very beautiful thing. The cross ratio perspective theorem. If concurrent lines L1, L2, L3, L4 meet a fifth line M, respectively in A1, A2, A3, A4, then there's an equality between cross ratios. The cross ratio of the lines is equal to the cross ratio of the points. So here are four lines, L1, L2, L3, L4. They're all concurrent. Here's a fifth line meeting these four lines at points A1, A2. Actually, that should be A2 up there, shouldn't it? Corresponding. A2 here, A3 there, and A4 there. Okay, so their respective meets. Then the cross ratio of these lines, which I remind you is computed by looking at direction vectors and cross products of direction vectors, and that's equal to the cross ratio of the 4 points, which is determined by ratios of vectors in the same direction. And beautifully, it doesn't matter which line you choose. Okay? So what that is saying is that this notion of cross ratio is perspective invariance. So if I'm looking at these 4 points from this point here, okay, looking at these 4 points, and then you move them over here, it's a perspectivity from this line to this line. But the cross ratio hasn't changed. That's why it's such an important thing in this story. Okay, and what's the proof of this? Well, here is the heart of the matter, okay? The heart of the matter really has to do with properties of the cross product. That's the nice way of saying it. So it really amounts to this diagram here, which is just a partial diagram. So suppose we have vector v1, v2, v3. These points are collinear a1, a2, a3. Then v1 cross v3, so v1 cross v3, that's going to be more or less actually twice the signed area of that triangle there. And v2 cross v3 in the denominator is going to be more or less the signed area of this triangle here. Okay, the first one going this way, the second one going this way. And then that is the same as the ratio of the vector a1, a3 to the vector a2, a3. So in the algebraic calculus course, you know, this is just a sort of a fundamental little computation that you make about the properties of the cross product. And then that thing there, when you stick that into both sides of this thing here, you see that that's responsible for this theorem. Now, when we had 4 collinear points, we had the idea of cross ratio of those 4 collinear points and the corresponding idea of harmonic range when the cross ratio happened to be -1. Okay, so it makes sense to have a corresponding definition for concurrent lines. L1, L2, L3, L4. They form a harmonic pencil, we will say, when their cross ratio is, again, -1. Now, here is an important kind of way that you get harmonic pencils. Okay. So if you have any two vectors, v1 and v2, v1 there, v2 there, and you form the sum, call it say v3, v1 plus v2, and you form the difference, v1 minus v2, call it v4, and L1, L2, L3, L4 are concurrent lines with direction vectors v1, v2, v3, v4. So that, say, might be the line L1, the line L2, the line L3, the line L4. Then these 4 lines form a harmonic pencil. That's a nice calculation for you to make. So that's an exercise, okay, to check that. So that's a very nice way of very quickly being able to show harmonic pencils. You just take two vectors v1 and v2 and then you form the sum and the difference, and there you go. The sum sort of divides this internally in the same way that the difference divides them externally. Okay, but there's an even more important example of a place where you get harmonic ranges and harmonic pencils that connects directly with our quadrilaterals and the basic thrust of what we're talking about here. So if we have a quadrilateral A, B, C, D, so we have 4 points, and we also have diagonal points x, y, z. So we get x by taking A, B, and C, D and seeing where they meet. We get y when we take B, C, and A, D and see where they meet. And we get z when we take A, C, and B, D and see where they meet. Those are the diagonal points of the quadrilateral. Okay, so now if we take one of those diagonal points, say x, then at x there are 4 lines which are coming in. There are the 2 lines which are the sides of the quadrilateral, the ones in blue, and there are also these other 2 sides in black which are lines to the other diagonal points. And the claim is that that's a harmonic pencil, that this thing here divides this sort of sector internally in the same way that this divides it externally. So AX, DX, and ZX and Y, so YX, or that should be an X. That is a harmonic pencil. And as an exercise, so first of all, proving that is a great little challenge. And another exercise, find the other 2 harmonic pencils. It's kind of obvious that, well, if there's a story for x, there should also be a story for y and a story for z. And then 6 harmonic ranges. Let me just show you one of them. So if we look at this pencil coming from x, then if we take any line there, say this one here, then where those 4 lines meet, say that one, that one, that one, and that one, those are going to be 4 points, and they're also going to form a harmonic pencil. This thing here is going to divide AD internally in the same way that this divides it externally. There's actually probably more floating around. So it's actually very rich. There's all kinds of harmonic ranges and harmonic pencils in this configuration. Okay, so we've got together a lot of good ingredients, basics of projective geometry. So now, next video, we're going to tackle this problem of the perspective image of a square. I hope you'll join me for that. I'm J Wildberger. Thanks for listening.